This is going to be chapter 6 from the book. And that is about ideals and quotient rings. In this chapter, we will repeat the construction which we presented in chapter 2 for the ring of integers, and in chapter 5, the previous one, for the ring of polynomials with coefficients in a field. Now we present this same construction in general for just rings, not necessarily these two instances of rings as ring of integers or ring of polynomials. To start with, let me recall something from chapter 3, where we already started to study general rings. So let R and S be two rings. And let F from R to S, a function, be a map, be a ring homomorphism. I recall, what does this mean? This means that f of a plus b equals f of a plus f of b, and f of the product ab equals f of a product with f of b. These plus addition and multiplication are in the ring R, while this addition and this multiplication are in the ring S. So basically, a homomorphism is a map which respects the ring structure. Let me recall, there was a corollary (311) which told us that f from R to S is a ring homomorphism then the image of F is a subring in S. Recall what the image of F is. Image F is the set of all elements F of A for all A's in R. Besides the image, and clearly image is a subring is a subset in S. The corollary claims that this is not merely a subset but a subring. This is a subset in S, which is a subring. This is a typical notation for image, although the book does not use it. I will use this sort of notations from time to time. Besides the image, there is another equally interesting subject to study, which is the kernel. So let me define the kernel of a homomorphism. F from a ring S to the ring R to the ring S. Image is a subset of S, and the kernel is going to be the subset of R. These are all elements which map to something interesting, and what is interesting, there is only one marked element in every ring, which is 0. So kernel of F is the set of all elements from the ring R such that F of A is 0 in S. By its very definition, the kernel is, of course, a subset in R. This is all elements in R which map to 0 in S. So definitely this is a non-empty subset, simply because we know that for every homomorphism F of 0 in R is 0 in S. Homomorphism respects the ring structure. Marked element 0 maps to the element 0. That was proved in chapter 3. Now, as soon as, well, first of all, let me show you that kernel, which I denoted ker F, again a notation which the book does not use, but I will occasionally use it, is, let me defend my statement that the kernel is also interesting. The book has theorem 611, which tells that the map F is injective. If and only if the kernel of this map is only this one, nothing else. Nothing but what it kernel contains nothing but 0, which the kernel absolutely must contain. You may immediately, from the definition of image, observe a similar statement about the map F. The map F is surjective. If and only if the image of F is all S. Well, this is a tautology. Well, it is obvious that when the image is all it can be, the map is surjective. From the definition of image, you do not need any proof of that. This is just a reformulation, an immediate consequence of the definition. As for this statement, you need a proof, but this proof is quite simple and you can find it in the book. So I will skip it. I cannot add anything to the proof presented in the textbook. This theorem tells us, especially paired with this statement, that the kernel is as interesting as the image is. Thus, we would expect that as the image is a subring of the target ring, the kernel should be a subring of the source ring for the map, and this is indeed the case. Let us prove that as a proposition. For a ring homomorphism, F from R to S, kernel F is a subring in R. So as image is not merely a subset of S, but a subring according to this corollary, the kernel, which is a subset of R, is going to be not merely a subset, but a subring. Let us prove this proposition. For the proof, I recall the criterion to check. Whether a subset is a subring. This is given by theorem 3.6, which we discussed briefly in chapter 3, and it tells us that a non-empty subset, say C in R, is a subring if and only if the two following conditions are satisfied. First, for any two elements in the subset T, or let me call it K for some reason, for any two elements of K, if A and B belong to K, then, so implies A and B belong to K, implies their difference belong to K. And the second condition to check is for any two elements in K, their product. So A and B belong to K implies AB also is an element of K. This is a criterion to check that a subset is a subring. Let us check that for the kernel of a homomorphism as a subset of R. The first condition, what does it mean? That A and B belong to kernel. That means, so A and B belong to the kernel of F. By the definition of kernel, these are those elements which map to 0. So that means F of A is 0S and F of B also is 0 in S. Thus, we can calculate F of A minus B, which by the property of homomorphism respects group structure, F of A minus F of B, which is 0 minus 0, which is 0 in S. Means again, by the definition, kernel is those elements which map to 0. A minus B maps to 0 means A minus B, this element, belongs to kernel of F. Let me also check the second condition. For the second condition, we again have A and B, so this checked, and A and B belong to kernel. Again, this means that F of A is 0 in S, and F of B is also 0 in S. Thus, f of product f of the product AB by the definition of homomorphism. This is equal to f of A, f of B, and this is 0s times 0s, which is of course equal to 0s. Checked. So we proved that this is a subring, but 0 times 0 is 0. Yes, indeed, that is true, but this is an overkill. This is an overkill. In fact, if one of them was not 0, we would still have 0 here. So we proved that this is a subring, but we can tell more about the kernel. So we can strengthen too. Namely, assume that R is any element from R, while A is still an element of the kernel of F. In this case, we still have. Now, by the way, I did not finish here. Sorry, I did not finish here. I put a check mark. I did not write the conclusion means. So AB, f of AB is 0, means AB belongs to kernel F. Now it is checked. Now let us take an arbitrary element from the ring and some element A from the kernel. Still, we have that f of AR by the definition of homomorphism. This is f of A times f of R, and A belongs to the kernel, so this is 0 in the ring S. Kernel is the elements which map to 0. Recall, here it is. Kernel is all elements which map to 0. So this is 0 times f of R. I don't know what is that. And I don't care what is that. Whatever it is, an element of S multiplied by 0 in S is going to be 0 anyways. Similarly, f of RA is f of R times f of A, which is f of R times 0, and this is again 0 in S. I need to check both because AR and RA may be different elements. The ring R is not assumed to be commutative ring, although probably all examples which I will show you pertain to commutative rings. So we have the kernel of any homomorphism is a subring which has an additional property. AR maps to 0, so means AR belongs to kernel. And that means RA also belongs to kernel. The additional property, the additional property is that if we multiply in any order AR or RA an element from the ring but by an element from the kernel, we produce an element from the kernel. Subrings with this extra property are called ideals. So ideals in the first place are kernels of homomorphism. Here is the definition motivated by this example. A subring I of R of, let me write it this way, of a ring R is called an ideal in R, or of R, if you want, provided whenever R is an arbitrary element of the ring and A belongs to the subring, then AR belongs to the subring and RA also belongs to the subring. Such subrings definitely exist as soon as we have homomorphisms from the ring. What we actually produced in this way with the argument above, with this proposition and this definition, is what the book calls Theorem 6.10. Proved in this way. Let F from R to S be a homomorphism of rings. Then the kernel of F is an ideal in R. Again, ideal by definition is a subring with extra property. We proved it is a subring in the proposition here, checked with the criterion, and we proved that it has an extra property. One typically calls this extra property absorption property. An ideal absorbs for an element. If we multiply an element of ideal by any other element, we get back to the ideal. Sorry, typo. So we multiply an element from ideal A by any other element, we got an element of ideal. That is the absorption property. Of course, not every subring is an ideal. Example 6 in the book, in section 6.1, tells us that not every subring is an ideal. As an example, they provide us with a subring Z as a subring of Q, integers as a subring of rational numbers. This is a subring which does not have the absorption property. If you multiply an integer by a rational number, you may produce an integer, but not necessarily. If you take an integer 2 and multiply it by some rational number, you produce that rational number, not an integer back. Not that some rational number. You take 2, multiply it by a third, and produce 2 thirds, which is not inside the subring. So it does not have absorption property. Thus, ideals are very special subrings. It is, so let me write it this way, ideals are very special subrings. It is easy to check, and the book does that. I will not repeat the calculations which the book does. Theorem 6.1, which gives us a criterion for a subset to be an ideal, a non-empty subset I, a subset of the ring R, of a ring R is an ideal if and only if the following two properties are satisfied. First, for any two elements which are elements of I, if A and B are elements of I, then, so this statement implies A and B belong to I, implies their difference also belongs to I. And the second is the absorption property. A in I, R in R implies AR in I and RA also in I. This is the absorption property. The proof uses the criterion which I just mentioned and used here, theorem 3.6, is used to check that that is enough, that this is if and only if conditions. For the proof, see the textbook for the details. If you cannot restore it on your own, I believe you can. Here is an example. Let me start with trivial examples. A ring R, any ring R, contains the subset which has nothing but zero element. Every ring has a zero element. This is a subset out of one element. It is a subring. This is zero ring as a subring of any ring, and it is very easy to check that this is an ideal. This set out of one element definitely satisfies the first property. 0 minus 0 is still 0, and there are no other elements to check. And what about the second property? Yes, 0 multiplied from the right or from the left by any element of the ring is 0. So this subset is an ideal. Another trivial example is the whole ring R. This is definitely a subring of itself. It is a subset, and it satisfies, of course, these two properties because the R is a ring. And this is also an ideal. These two examples are trivial. They are called trivial ideals in the literature versus proper ideals, which are not those. Here is another example, less trivial. They are sometimes called trivial ideals. Sometimes only this ideal is called, only the whole ring is called trivial, not zero. Depends on the literature. Here is less trivial, non-trivial examples. Oh, I wrote in plural, so I can avoid writing examples altogether. So consider the ring Z, the ring of integers, and let n be an integer, any integer. Clearly, Z contains the set of all multiples of n This is an ideal. It is easy to check again the difference of two multiples of n is still a multiple of n, and if we multiply any integer by a multiple of n, we produce a multiple of n. So this is an ideal. You produce the trivial ideal if n is 1, and you produce this trivial ideal when n is 0. You produce this trivial ideal when n is plus or minus 1, a unit. Plus or minus 1, all integers are all integers. Either plus 1 or 1 times all integers are all integers, and negative 1 times any integer is still any integer. So trivial, this ideal becomes trivial if n is 0 and n is plus or minus 1. Trivial, one of them. Similarly, you may start with the ring of polynomials and consider a polynomial p an element of this ring. Again, the ring of polynomials contains a subset of all multiples of polynomial p. By the same token, this is an ideal which becomes trivial if p is 0 in F, or this is the same thing as 0 in the ring, or P is a unit, meaning a non-zero element of F. As you remember, these are the units of this ring. It is also easy to see that all polynomials multiplied by any unit, similarly to plus 1 or minus 1 here, are still all polynomials. And all polynomials multiplied by 0 is just 0 polynomial, nothing else. From these two examples, one can generalize, and from the last two examples, one can generalize theorem 6.2, let R be a commutative ring with identity. For any C an element of the ring, so both Z and polynomials are commutative rings with identity. For any element of the ring, the set of all multiples of this element. Now it doesn't matter, since the ring is commutative, it doesn't matter RC or CR. For all R in the ring is an ideal. The set of all multiples of any fixed element is an ideal. Trivial ideal. This ideal becomes trivial when C is 0 in the ring, or when C is a unit. When C is a 0 when C is the 0 in the ring, this is this ideal. When C is the unit, this is the whole ring. Otherwise, it is a proper ideal, something in between, bigger than just this minimalistic example, smaller than this maximalistic example, some ideal. We call these ideals principal. So this is, by definition, principal ideal. All multiples of an element of the ring is an ideal, and this is a principal ideal. This ideal, any such ideal is called principal. The proof goes exactly along the same lines as in the examples. We check with the criterion, which is theorem 6.1, that I satisfies the two properties, thus is an ideal. In fact, even more generally, theorem 6.3, again, in a commutative ring with identity, and let C1 up to Cn be a collection of elements of R. Just n elements of the ring R. Then the set I defined as all sums R1 C1 plus up to Rn Cn for R1, R2, whatever, Rn, all any elements of R, is an ideal. Again, the proof runs along the same lines. This is a very straightforward generalization, and this is called a finitely generated ideal. So you may read the proof of this last theorem, and then, oh, this theorem is a special case when n equals 1. These examples are special cases when R is either Z or the ring of polynomials. It is so I will not repeat the proof from the book here. Instead, I will show you an example. So examples 9 and 8 tell us, present a finitely generated ideal which is not a principal ideal. In these examples, R is the ring of polynomials with integral coefficients. Z, the ring of integers, it's a ring, it's not a field. Polynomials with coefficients in Z. We take for C1, we take 2. This is a polynomial with integral coefficients of degree 0. And C1 or C2, we take x, which is same thing as 1 times x, and 1 number 1. And this is a polynomial of degree 1 with integral coefficients. 1 is an integer. So constant polynomial, polynomial of degree 1. The ideal which we want to consider is this one, finitely generated by these two elements. So it looks like C1, 2, G plus X, F. Let me renumber them so that this is this one is going to be C1 and this one is going to be C2, and then I write it to X F plus 2G as R1 is F, R2 is G, F, G, any polynomials in the ring, any elements of the ring, any polynomials. it is easy to see. This is exercise 15 in the book. An alternative characterization of this set I. I is the set of all polynomials with polynomials in with integral coefficients with even constant term. Oh, indeed, the constant term of this polynomial is 2 times the constant term of g. This polynomial has no constant term. This polynomial has constant term of 2 times the constant term of g, which is even. At the same time, it is not difficult to present any polynomial with even constant term in this way with some f and g. Say, so I will show you only one direction. One direction I told you, it is very easy to see that the constant term is always even. And conversely, let h be 2c0 plus c1x plus cn x to the n. An arbitrary polynomial with even constant term c naught up to cn are all integers. This is any polynomial. You can write this way, any polynomial with even constant term. Then you can write h as x times f plus 2g, where g with g is equal to c naught, whatever it was. So this is a constant polynomial. And as to f, it is either 0 if degree h is 0 or h is 0 polynomial, or if this is not the case, then f is c1 plus c2 x plus c n x to the n minus 1. I have two cases here because if n is 0, I cannot write n minus 1. We don't have 1 over x. We don't have negative powers of x here. We have only positive power of x, which means, if you remember, this means that x's here are just a way for bookkeeping. Polynomial is the ordered collection of its coefficients. X is for bookkeeping, for ordering coefficients, not a variable still. So it is in the example 8, it is proved that this is an ideal, that there is nothing to prove. That is an ideal immediately from theorem 6.3. So there is nothing to prove here. Example 8 precedes the theorem, so they proved it by hand. You can immediately see from theorem 6.3 that I is an ideal. Finitely generated ideal. And now a more interesting statement which the book somehow does not emphasize on, that this ideal is not principal. So let me prove it, continuing this example as a proposition. I is not a principal ideal. That will tell us that not every ideal is principal. We are in a general situation. You will not find examples of non-principal ideals in this ring, which were the focus of our consideration. Neither Z nor polynomials have non-principal ideals. Every ideal, in fact, in these rings, we'll later discuss that in detail, is principal. At the same time, we do have in more general rings examples of non-principal ideals, and this is an example of an ideal which is not principal. This ideal I, this one, in this ring, is not a principal ideal. Let me prove that. So I want to emphasize thus not every ideal is principal. No, put it differently. Not every ideal in an arbitrary ring or there are rings which have non-principal ideals. Let me prove that I is not a principal ideal. So, assume for the sake of contradiction that, so assume that I is principal. or multiples of some element f. So then, we wanted such P cannot exist. How do we prove that? Oh, in particular, so these are all P times a polynomial are all elements of I. So 2 is an element of I. The set of all polynomials with even constant term, 2 is even, or take g equals 1, f is 0, both polynomials, constant polynomials, and you get 2 as an element. By the way, x is also an element of I. You take g equals 0 and f equals 1. Both, again, are polynomials in this ring. So 2 is an element of I. Thus, 2 must be equal to P f1 with f1 some polynomial but this is a product of two polynomials. So degree of this polynomial 2 is 0, and so degree of the constant polynomial 2 should be equal to degree p plus degree f1. And this is 0. Nothing too bad. That still can happen. This is 0 as a sum of two non-negative integers. But that can happen simply if both degree p and degree f1 are zeros. So that implies that degree p is 0. Thus, p as a constant polynomial. So if p exists, then it must be constant. Also, we can write x. X is also an element of I. Thus, it must be that x is p times f2 with some polynomial f2 with integral coefficients. Again, I take degrees. In this case, degree x is degree p plus degree f2. We already know that degree of the polynomial p is 0. This is 1. This is a polynomial of degree 1. Is 0 plus the only chance for f2 is to have degree 1. Thus, we can rewrite this equality as x. So let me say that degree f2 is 1 implies f2 is ax plus b. A not a 0. A and b are integers, a non-zero. So this and p is a constant polynomial. Constant polynomials are reduced to their constant terms. These are just integers inside polynomials. So we have that x is equal to p times f2, which is ax plus b. Or, equivalently, x equals p ax plus b. This is an equality. X is not a number. It is a way of bookkeeping. So this means that constant term of this polynomial is 0. Constant term of this polynomial must be 0. Implies b is 0 and x is equal to pax, or immediately from the same bookkeeping argument, the coefficient of x must agree, meaning pa is 1. pa is 1 implies p, they are both integers. So let me recall, write it here, p and a are both integers. The product of two integers can be 1. Both of them must be plus or minus 1. Implies p is plus or 1 or minus 1. 1 or p is negative 1. In both, now look here at our principal ideal. If the ideal was principal, then p should be either 1 or negative 1. In both cases, this ideal is the whole ring. If p is 1, these are simply all polynomials. P is negative 1, these are negative all polynomials, so also all polynomials. So in either case, I is the whole ring. Would be okay, but we know that this ideal is not the whole ring. This is the set of all polynomials with even constant term. The ring contains polynomials with odd constant term. So that is not true because I is the I is the set of all polynomials with even constant terms while the whole ring contains polynomials with odd constant term. This is a contradiction, and as we wanted, the contradiction implies that such polynomial does not exist. We found that if it exists, then it must be 1 and negative 1, but it cannot be 1 and negative 1 because that gives us a wrong, both give us wrong I. So it does not exist, and we conclude that that there exists not every ideal. There are rings, this one in particular, which has ideals which are not principal. That allows me to make a remark about the terminology. So, terminology. The word ideal was introduced by Dedekind, a German mathematician of 19th century, as an abbreviation for ideal numbers. He was thinking about rings as sets of numbers and about elements of rings as kind of numbers in this or that sense. We do not take this point of view anymore. But this was the original point of view long ago. For us, elements of a ring are just elements of a set. And he thought about every ideal as a principal ideal. He knew pretty well that not every ideal is principal, so he thought that this is sort of principal ideal generated by an ideal number. So he clearly understood that, and immediately understood that, for example, in this case, the ideal is not principal, but it behaves like all multiples by a polynomial which does not exist. An ideal looks like all multiples of an ideal polynomial. And that was the introduction, especially to the case when ideals are not principal. He introduced the idea of ideal generator, ideal number, ideal polynomial, which is multiplied by any element, and the set is an ideal. Ideal in this context means which actually does not exist. So, generated by ideal number. An element of the ring which actually does not exist. That was why this word ideal came into the existence. And the idea of ideal, pun intended, is ubiquitous in ring theory, and we will deal with that. We'll try to understand where does it lead it. So, all right, let me finish the fragment here, and we will continue our study of ideals in the next fragment. Thank you for listening.